Anyway, so thanks for coming out this morning. My name's Jed Sundwall. That's how I say it. My ancestors are Swedish, but I'm American. I live in Germany now. This is actually only my second time in Stockholm. But by the time I go home, I'm going to perfect pronouncing my name. Sundwall? Sundwall. So anyway, if you can help me with that, I'd appreciate it. So I run the Open Data program at AWS. We've got a team that we're a global team. We work with customers all over the world. We mostly work with government customers who have large volumes of data that they want to share publicly. So we work a lot with like big scientific agencies. We work with NASA. We work with a lot of meteorological offices, like the Met Office in the UK. And then obviously today we're going to be hearing from Rupe from the Finnish Meteorological Institute. And open data is really important to AWS because, like I said, we have a lot of customers that are on the public sector side that supply open data. On the other hand, we have a lot of customers that are on the demand side. So they need data from the government in order to be able to build their own products and their own services. And so having data in the cloud really allows these customers to interact with each other much more effectively. And the way we describe our work is so we work with our customers to help them understand how to stage data for analysis in the cloud. And I think this might be some of the more interesting part for all of you who are attending is understanding what we mean when we talk about staging data for analysis in AWS and why working with data in the cloud is different than I guess what we call like traditional ways of sharing data. Now, one way you can really get an idea of what we do and who we work with is by going to what we call RODA, which RODA stands for the Registry of Open Data on AWS. You can just go to registry.opendata.aws. And what you'll find there are a number of data sets that are made available on AWS. They're provided by the data providers, so the organizations that create the data, like NASA or Deutsche Börse, which is the German stock exchange, even the IRS, which is the tax agency in the United States. It's one of the most beloved government agencies in the United States. But they share some data through our program as well. And what you'll find there, first of all, is information about the data sets that are available, how to access them, and then usage examples. So one thing that we really try to keep track of, and we use to sort of measure the effectiveness of our program and what we're doing, is if we put data on the cloud, we want it to be put to work. We want it to be used. And if we work with an organization to put some data on AWS, if somebody builds a demo or an application or something like that on top of the data, we consider that a huge win. That's evidence that the data is actually useful and that people have something to do with it. So anyway, I encourage you to check that out. Now, we have I want to take a minute to sort of explain some of the theories behind what we do and why we think open data on the cloud is so important. So number one is just we always talk to our customers who work with data, who are researchers that have ideas of stuff they want to do. And what we've learned consistently is that data acquisition is a huge pain, right? So there are many instances where researchers, if they have an idea of something they'd like to do, they know that data exists. Perhaps the government has data that they could use for their research, but getting that data is really hard. So either it's on a very low capacity FTP server that can't handle a lot of requests, or it's not connected to a good network. You have to take a long time to download it. In many cases, the data is on tape, right? So the data might be on tape somewhere, and for you to get it, you actually have to maybe call someone on the phone, which, if you're like me, I'd rather just not do that. So people are starting to expect that you should be able to get data just by looking for it online and accessing it via an API or some other means. And if data is locked up somewhere, it's going to inhibit work. And we hear about this from researchers all the time where they're saying, I have an idea for a project, but getting the data is too hard, so I'm just going to think of something else to do. And there's this book called Data Driven. It's a very short book that I really like by DJ Patil and Hilary Mason. DJ Patil he was like the chief data scientist of the United States. This is under a previous administration. But anyway, they said, data has to be, 80% of the data scientist's work is just spent preparing data for analysis. And every time I share this quote, I don't think there's like any evidence for that 80% number. I don't know if they did any surveys on this, but this 80% number gets thrown around all the time. And nobody's ever disagreed with me when I share this. In fact, a lot of people say it might be even more than that. Now, this idea, this work of cleaning up data or just preparing data to be used, we have a term for this at Amazon we use all the time. We always talk about undifferentiated heavy lifting. So undifferentiated heavy lifting is all of the work that you have to do that doesn't differentiate you from your competition or from your peers, but that you have to do. And it's a good example of this is if you're thinking about managing IT infrastructure, buying a server, installing it onto a rack, plugging it in, cooling it, securing it, configuring it, all that sort of stuff. That's undifferentiated heavy lifting. That's stuff that you and all of your competitors have to do that's keeping you from doing what you're really good at. And what we do at AWS, the way we approach all of our products is thinking, okay, what is the undifferentiated heavy lifting that our customers have to deal with, and can we take that off their plates? And so if you think about, just using EC2, our server products, you get access to a server instantaneously without having to order a server and configure it and things like that. Same thing with storage. If you use Amazon S3 to store things, you never have to worry about backups. You never have to worry about disks failing and replacing failing disks. And you also don't ever have to worry about running out of space. You just get to use storage. And so that's the way we think about undifferentiated heavy lifting, and we apply the same sort of thinking to data access. So when data is available in the cloud, you don't have to really acquire it. So the data acquisition process is almost flipped. Instead of downloading data to whatever compute resources you have, you just deploy compute resources in the cloud next to the data. And this creates a lot of advantages, but the main being, it sounds very simplistic, the data just doesn't have to move very far for you to analyze it. When you're dealing with big data analysis and you're starting to deal with terabytes, maybe even petabytes of data and millions of objects and things like that, the transit of those objects and of that data from wherever it's stored to wherever you're going to compute on it becomes a huge bottleneck. When you're talking about big data, the biggest constraint isn't necessarily your compute capacity. It's how you manage the throughput from wherever the data is stored to where it's being used. Now, we have here, I'm not going to go into any details of sort of like what all of these different products are, but we have a lot of products. And so, which brings me to this point, is that when data is made available in a cloud environment, you get these really remarkable advantages that you don't get if you're making data available in a way that you require people to download it before they work with it. And one of them is, I'm actually going to start with the one on the top right, which is new services and tools. So we're continually adding new services and tools to the platform that allow you to do things with data at much lower cost or in new ways. Some examples of these are Lambda, which is our serverless compute service. We also have a thing called Amazon Athena that allows you to run SQL queries against really large volumes of data stored in S3. These services didn't exist a few years ago. But what this means is that if you had your data already in AWS, the day these services came out, your data just became more valuable, just instantaneously, because you suddenly have access to new tools that you can use to work with the data. The other one is that if you work with a government agency and you want to, your mission is to put your data to work and make sure lots of people can use it. We have well over 1 million users worldwide, and a massive user base of startups and enterprises, other government agencies, and they all use AWS, and there's a large community of AWS users that exist that you can reach, and they can support you and take advantage of the data. And then these last 2 points are kind of the same, because time basically equals money. But if you can do research more quickly, you can do research at much lower cost. And one sort of just basic fact here is that previously, if you wanted to work with 100 terabytes of data outside of the cloud, you had to have 100 terabytes of storage. Like you actually had to buy 100 terabytes of hard disk space, and then you'd have to figure out how to copy that. That costs time and money, and if data is available in the cloud, you don't have to worry about that. So I'm just going to talk really briefly before I hand it off to Rupe about Earth on AWS. So we have we emphasize quite a bit with our program hosting Earth observations and meteorological data, and you can find out a lot about that stuff at aws.amazon.com/earth. But one example here of what we've done is we started making Landsat data available. So this image you're seeing here, this is New Zealand, but it includes infrared data that highlights vegetation, so that's why it looks like this. It's a false color image. It just looks very cool. But you can use this satellite imagery to identify things like vegetation. It's used for a lot of agricultural research. And typically, the way you would get Landsat data from the government that provides it is you download a gigabyte object every time you wanted to see part of the planet. And what we did is we were like, okay, well, that gigabyte object actually included a bunch of files inside, a lot of which people didn't always need. And so what we started doing, we said, okay, we're going to put this data in the cloud, but we're going to make it available in a way so that people can get just the data that they want without having to download an entire gigabyte at a time. Like I said before, this network throughput, that's really the constraint when you're working with big data. And what ends up happening here is that, so this is one researcher who what you're seeing on this graph, there are 90,000 points, and each point represents an analysis that he was doing on Landsat data. On the left-hand side, you can see the points that are higher up. It's because they took more time. So the y-axis is time, it's seconds. So they would take somewhere between 350, 400 seconds each time to do the analysis. When we made the data available on AWS and the way we did, each analysis went down from about 300 seconds, 300 to 400 seconds down to about 20 seconds, okay? So, the solid order of magnitude lower. And we added this up, we did the math and figured out, we saved this one researcher 250 days of his time just by cutting out that network throughput. And then what's remarkable about this is that when the data is available in this way, it allows people to build services that can interact with it really, really quickly without, again, having to move the data. What you're seeing here is an animation of a JavaScript app. This is entirely browser-based. You just click around in your browser. There's no server running behind this app. What's going on as you use this interface in your browser is that it's using Lambda, which is what I mentioned before, which is a serverless compute program. So what you're doing in your browser is you're triggering Lambda functions, and these little Lambda functions are going to S3, gathering imagery, processing it, and turning it into something you can see in your browser in a tile in real time. And it's extremely inexpensive. But then more significantly is, it allows people to do things like this, like what Zooniverse did. Zooniverse is a really interesting group out of Oxford, and well, they're global, but they do this great work crowdsourcing data analysis. And so after hurricanes and earthquakes and things like that, they grab the satellite imagery that we have available in the cloud and immediately make it available to people so they can say, okay, this is the latest satellite imagery that we can see after this earthquake. Can you help us identify roads that have been blocked or other damage caused by this? And then we're going to talk about weather, so this will be my segue to Gruppe. We have a collaboration with NOAA in the United States, it's the Weather Administration of the United States. We started making radar data. So this is a radar tower, and we started making radar data that they produce available on AWS. And they did this interesting analysis for us. What you're seeing here are, I guess this is from 2013 to 2016, the same period of time. All the NextRad radar data that they had been serving out was around 100 to 150 terabytes during this period of time. Once we made it available on AWS, that shot up so that they over doubled how much data they're able to serve in total, and also reduced the strain on their own servers. So that blue part of that last bar is their own servers serving up data. We started serving up all the data for them, and we were also able to serve a much larger volume. And what this showed was kind of like, this is a demonstration of what I was saying before. When data's hard to get, it stops research. But when data's easy to get, people will do cool stuff with it. And we had this interesting experience just a few months ago where an article came out in Nature where some ornithologists included this line that really surprised me. It said, recently NOAA and AWS made available one of the largest data sets describing animal movement ever compiled. And I was like, that's interesting. I don't remember doing that with NOAA. But they said, it's the NextRad radar archive. One really cool thing about opening data is that when you open up data, you make it available to a more diverse audience that has a different perspective and has different needs and ideas of what they can do with it. it turns out that you can see birds in radar data. So typically when you look at radar data, you see things like storms, hurricanes, and stuff like that. But what you're seeing here in this animation on the right is a flock of birds waking up in the morning and flying out. And so you can see that in radar data. And when we made the data available from NOAA on AWS, it suddenly unlocked a ton of research from ornithologists. And they were able to do the first, one of the first continental scale analyses of animal, migration patterns, ever done, which is really exciting and really gratifying, and just a really nice surprise. And just again underscores the fact that when you can make data easier to work with, you're going to unlock a lot more innovation and value from that data than you might have ever anticipated. So I'm going to stop there, and I'm going to bring up Ruben's slides.
I'm going to tell you about our open data and open source software and how we are distributing the data. Also, we are Amazon Web Services public dataset program. First, I'm going to tell you something why we are doing this, and then more like how we are doing this. Finnish government and Finnish Meteorological Institute also have a very strong open data initiative. Since 2013, basically all our data has been open. And since 2016, FMI also started to release open source software. And basically, from now on, all the software we are producing will be open source. There are some exceptions, but basically, in principle, everything we do will be open source from now on. So, why we are doing this? The world is changing, it's always changing. And because of that, our role of meteorological institutes is also changing. And that change caused us many challenges. To mention a few, we need to ensure authoritative voice in warnings, because there are many providers giving warnings. But we need to ensure that we are giving responsible warnings and people are actually trusting them. Then we need more agility, more efficiency in development and operations. We need more speed kind of for that. And most importantly, we need to ensure the impact of produced information, because it doesn't make sense to do all the analysis and produce all the data if it doesn't have an impact. Our ecosystem is also changing. We are moving we don't charge for the data anymore. We have open data. If we charge for something, we charge for service. And I think this is the same for private sector also. And we are moving from closed ecosystem to open ecosystem. That means that meteorological institutes doesn't control the whole value chain anymore. They release the data, but they don't have a control after that. And that's kind of challenging, but that also helps us, of course. And this means also that private sector in total is taking more and more responsibility of the value chain. Yeah. So, open data and open source software can help us a lot in this changing ecosystem and to answer these challenges. Traditionally, our field, meteorological and climate field, and in many cases, in many countries, hydrology as well, is very good, or have been very good in collaboration when it comes to gathering observations and running numerical weather predictions and sharing that data. But there are actually very many steps before you can actually see the weather forecast in your mobile phone or anywhere you are looking at. There are, for example, post-processing and interpretation and visualizations and creating and sharing, running these applications. And many of these steps are this undifferentiated heavy lifting, because all the entities, all the companies, and all the meteorological institutes are doing mostly the same stuff, especially when it comes to post-processing and interpretation. So we need more collaboration there. And this open data and open source software, and both, it makes that collaboration easier. For example, if you find some good data produced by, for example, other meteorological institute or some company or whoever, you can just evaluate it, and if it fits for the purpose, you can just use it. And if you need some modifications to the data or to the software, this works for both data and software, you can modify it. Or you can find some third party to modify it. This way, open data and open source software also prevents from vendor hooks. And of course, especially open source software, but also open data, boost the development, because everyone is contributing to the same source code and same repository, so everyone doesn't have to do all the changes themselves. This way it also eases public-private partnership. Of course, all this kind of collaboration between public entities and private entities is much easier when the data is open and software is open. There are still some licensing issues, but they are much easier when it's some open license. And this open data, from private sector view, this open data provides seamless access to weather and climate data information from multiple data providers. Because at the moment, for example, Sweden and Finland, they are producing their own weather forecasts. It's more or less the same, but anyway, it's different. And if you are if you need some weather information from both countries, if you want the best weather information, you need to take something from Finland, something from Sweden, and so on in other countries also. But if everyone has open data and is distributed properly, it's very easy to get the data from different sources and use it. One reason why we need this open data openness is that data is valuable only when it's used. And this maximum coverage requires several different channels and services. And for small organizations like us, or relatively small organizations, we can't handle all the channels. There are coming new channels very often, and they are coming and going, and we can't handle them all. But this open data really helps here, because we can just provide the data, and we can trust that someone else is actually handling all these channels. Putting this same thing in other way, data is valuable only when it's used. Because if we think when we are successful as a government institute, meteorological services in every country are successful when weather and climate don't cause unanticipated, unwanted impact to society. And we may know that there's bad weather coming, or sea level is rising or something like that. We may know it, but it doesn't help that we know it if it doesn't have an impact, if this information isn't distributed. So we need to distribute information as widely as possible. And this way, open data lowers the usability barrier and increase the data use. But open data here is not actually, it's not enough, because our data and our field is very complex. We have huge data volumes, often updating data, complicated data formats, complex domain, and so on and so on. So we need actually to provide the tools to handle the data properly also. And that empowers third-party users easily and fast to utilize the data. And this way, providing these proper tools also ensures that information is analyzed correctly, regardless of the channel and services which are used. Open data and open source software empowers science as well. Of course, it provides easy access to the data, as Jeff described, and it makes analyzing open source software makes analyzing the data easier, because and correctly analyzing data easier, because researchers can access the tools also. But there's also one other aspect in open data and open source software science. It makes science repeatable, because also other researchers can access the very same data which is used in the research, and very same tools which is used in the research. Okay, that's about philosophy. Going to practice. As I said, FMI, Finnish Meteorological Institute, has a very strong open data initiative. Since 2013, basically all our data has been open. In 2013, we kind of tried to open everything we have property rights to open. And that means that in our open data portal, there's very vast data content. There are weather observations, historical weather observations, climatological data, climatological scenarios, weather prediction data, weather forecasts, marine observations, marine forecasts, air quality data, and so on. Lots of data. And all the data is provided in machine readable format. Later on, we added some user interface for the most popular data types, namely weather observations. I think there's nothing else there. But all other data is only in machine readable formats available. Sorry. And actually, we are using Inspire European Union Directive as a framework for our open data portal, and we use the very same open data portal for Inspire and open data. And that means that we share certain type of metadata, we use certain type of services, WFS, WMS, and CSW, and we use certain type of data models. And we actually provide the same data in different type of data models to maximize interoperability and client support. We used to have a registration, and we had some usage limits so that everyone can download everything once, but we don't want or didn't want to be a backend for services. But we decided to get rid of that. We saw that it's very inconvenient for our users. Of course, this kind of registration, although it was easy, it removed anonymously, and it's kind of extra step. But maybe more importantly, it was very hard because you actually couldn't share some code snippets or already working software in GitHub or in Pilot or anywhere, because you didn't want to share your API key, which was needed. So that's actually a very remarkable thing. And also that broke all the links. You couldn't link to the data in the presentations or applications or anywhere. And that's also a remarkable thing. So there's no registration anymore. You can just go there, get the data. We are doing quite good. In our open data portal, there's almost 12,000 users, and we get a little over 800,000 data downloads per day, meaning almost 10 requests every second. Considering we are only quite small country, I think this is very well, but not enough. Because data is valuable only when it's used, only when it reaches relevant audience. And maximum coverage requires several different channels. So we decided also to join Amazon public datasets. That's for the opportunity to make things easier for our developers. That means that part of our weather data at the moment, weather forecast, is divided also in Amazon's web service cloud platform, S3. Well, this is the 2-year pilot. It started in 2017, in May 2017. And there's weather forecast data for ground level, surface level, which is normally used, but also for upper air levels, which is used for example, aviation. And for several post-processing steps. Our objective here is most importantly to increase utility of the data, as I've said many times already, and also support public-private partnership to make things easier, doing things together with private entities. This is available for anyone, but this is especially convenient for users who need the whole data of weather forecast, like for example creating map visualizations or some post-processing or something like that. And license and content of the data is very safe in our open data portal and Amazon web service. So, covering Europe, weather forecast, 7.5 kilometers, that updates 4 times a day, and it's 2 days ahead, weather forecast with 1 hour concept. And there are several weather parameters, I think 17 weather parameters available. You can access the data via buckets, and you can browse the content with your web browser. And there's also a simple notification service available so that you can subscribe and get notification whenever there's a new object uploaded there. If you are more interested, please see the documentation here. We have been going for 1.5 years, roughly now. How well have we succeeded? Before giving actual numbers, I want to give you some context. This plot here shows how requests are divided in our FMI open data portal for all datasets. Left column is for point requests, and this is for 1 month, September 2018. There are 3 different, the same data is available in 3 different data formats, in 3 different point data formats. And from there you can see that we get roughly 25 million requests, point data requests in the open data portal. And right invisible column is for grid requests. That means that we can provide the data in a kind of raw format, whole field, 2D or 3D field, huge amount of data, or every request is a huge amount of data. The column itself is invisible, but it's still over 40,000 requests distributed. The whole data is distributed there. It's still a remarkable amount of requests. I forgot to say, the left column means, in most cases, for example, weather forecast case, it means that we interpolate the data into that exact location for our users, which they are interested in, and give simple time series. while in grid version we keep the old raw data in binary format. But to compare AWS and our open data portal, we need to look at Hero weather forecast requests because we have all the Hero data available there. And this plot is how requests are divided for Hero data in our open data portal. In my open data portal, and it's roughly the same. We get 6.5 million point requests to Hero and 32,000 grid requests in binary format. And now, if we want to compare AWS and our open data portal, here's just number of requests. Blue line is FMI open data portal. Yellow line is Amazon Web Services. We get lots of more requests in Amazon Web Services, but this is not the whole story because the data in Amazon Web Services is divided so that every weather parameter is in separate file. And in order to download the whole model run, user needs several requests, 17 requests per model run. And FMI Open Data Portal user can fetch everything with just one request. So we have to normalize this data a bit. And if we assume that every Amazon AWS user download everything from one model run, we get this plot. And from here, green line is Amazon and blue line is FMI. We can see that we get almost double as much requests to Amazon than FMI. So it's kind of double more popular than FMI. Actually, I'm quite sure that not all users download everything because some of them are just interested in temperature and some just wind and so on. That means that this Amazon is even more popular than this plot shows. And if we add trend line for this graph, we can see that Amazon popularity is increasing quite rapidly, and FMI popularity is going slightly down. This has been Amazon has been available just 1.5 years, and FMI Open Data Portal has been available since 2013. And getting these requests changes are not very fast because coding this kind of infrastructure and coding this software is slow, and we get new requests only when people are actually doing something, and it takes time. So at the moment we get roughly 54,000 requests per month to Amazon. That would mean if everyone downloads everything, that would need roughly 300 users to fetch the whole data. I think it's more. Actually, daily figures, these are monthly amount of requests, but actually daily figures changes a lot, so we need lots of development activities there. This is quite young pilot, just 1.5 years, so people are still developing things, and I think these amounts will increase in the future quite much still. So, for binary data, S3 is the most popular channel, it's clear, but for all requests, point requests are by far the most popular type of requests. To give you one example how this can be used, I will tell you about Finnish startup company, Linheat. Linheat provides a software solution for optimized heating in centrally heated buildings. And they generate a building-specific heat demand forecast goes few days into the future, and they can optimally adjust heating power at all times based on a generated model. And for that, they need also weather data, and they are using this Hirland weather forecast produced by FMI. And as they are doing all their processes in Amazon Web Services, this S3 is very convenient for them. They are also running kind of post-processing model to the weather data, so that's also very convenient. This is very convenient way for them. And this way they can actually build a very they was able to build this infrastructure very fast up and running. Okay, as a conclusion, you need to be open to have an impact. This is especially important for public sector, but also I think it's also for private sector as well. And as I said many times, maximum coverage requires several different channels and services.